Good morning, everyone. Today we are presenting our project titled CNN based disease detection. This project was developed as part of our neural networking and deep learning course. Our objective is to classify images using convolutional neural network to automatically classify plant leaf images into different diseases and health categories. Our presentation follows the complete machine learning pipeline. We will first discuss the problem, motivation, followed by the project scopes and objectives. Then we will explain the dataset and pre-processing methodology following CNN architecture and training processes. Finally, we will present the model result, analyze its error, and discuss its real-world applications, limitations, and future improvements. Plant diseases can be classified, or to say, plant diseases can significantly affect crop production, so early detection is important. Our plant project addresses this problem using a CNN based image classification approach. We selected 10 plants and 10 plant health categories across 4 crops: tomato, potato, apple, and grape. Using the plant village dataset, the images were pre-processed using to train the CNN from scratch. The final model achieved 87.77% accuracy and a Marco F1 score of 87.89% on 687 unseen test images. One of the main challenges we observed distinguishingly visually similar diseases, particularly tomato early blight and tomato late blight. Plant diseases can spread rapidly and can lead to significant crop economic losses. Traditional disease identification generally depends on visual inspection and agricultural expertise. This can become difficult when expert assistance is unavailable, when rapid diagnosis is required. CNNs are particularly useful for images based on problems because they can automatically learn visuals from features such as edges, textures, spots, and lacing patterns. Therefore, our project explores whether a compact CNN can provide effective automated approach for plant disease classification. The problem we are addressing is difficulty of identifying plant diseases quickly and consistently through manual inspection. Our approach is to take a single RGB image of a plant leaf as input and classify it into one of the predefined plant health categories. The idea is such that the automated system could eventually provide an accessible first level screening tool for the disease identification. Our project has several objectives. We first wanted to talk and build a CNN based image classification pipeline. Second, we prepared a dataset containing 10 classes across 4 crops. We also used augmentation and regulation techniques to improve generalizations. For evaluation, we used accuracy, precision, recall, and F1 score. We also analyzed the confusion matrix and class wise performance to understand the strength and the weaknesses of the model. Finally, we identified limitations, possible improvements, and further development. For our dataset, we used a curated subset of the plant village dataset. The original plant village dataset contains many plant diseases categories, but for this project, we selected 10 classes covering the 4 crops. For tomato, we used early blight, late blight, and healthy. For potato, we used early blight, late blight, and healthy. For apple, we used apple scrub and black rot. For grape, we used black rot and healthy. For after pre-processing, we had 4,575 unstable images. The images were resized to 128 by 128 pixels with 3 RGB channels. We then divided the data into training, validation, and test you set using a 70, 15, and 15% split. Handing off to Kaustav. Now that we have discussed the problem and the data set, Kaustav will explain how prepared the images and how designed the CNN methodology to solve the classification problem.
The scope of our project is focused specifically on still image plant classification. We worked with 10 predefined classes covering 4 crops. The complete pipeline includes image pre-processing, model training, evaluation, and performance analysis. However, there are few things which are outside in the current scope. We are not performing real-time video monitoring, disease severity grading, or production level mobile deployment. We also use only 10 class rather than the complete plant taxonomy. SDG mapping. Our project also has relevance beyond technical aspects. It connects with SDG 2.0 Hunter because early disease detection can help protect crop yields. It relates to SDG 9 because we are applying deep learning technology to agricultural problems. It also relates to SDG 12 since better disease identification could potentially reduce the crop wastage. Finally, it connects with SDG 15 because healthier crops and more targeted disease management can contribute to healthier ecosystem. Now we move on to the literature. Before developing the model, we reviewed existing work in plant disease classification. Earlier studies using plant village demonstrated that CNN can achieve strong performance on plant disease images. Research also explored deeper architecture and lightweight CNN approaches. An important observation from previous work is that visually similar disease classes remain difficult to distinguish. This is relevant to our project because we observed a similar problem, particularly with tomato early blight and tomato late blight. So, the literature helped us understand both the potential of CNN and the challenges involved in this type of classification. Pre-processing and data augmentation. Before feeding the image into CNN, we performed several pre-processing steps. First, where first images were converted into consistent RGB format. They were resized to 128 by 128 pixels so that every image had same input dimensions. We then normalized pixels values from 0 to 255 into the range to 0 to 1. The corrupted or unreadable images were removed and the number of images per class was controlled to keep the dataset manageable. During training, we also applied random horizontal flipping, rotation, and zoom. These augmentation techniques expose the model slightly different versions of the training images and help improve generalization. Model architecture or CNN architecture. This is the core of our deep learning model. We developed a custom CNN trained from a scratch. The input is a 128 by 128 image. The model first applies data augmentation and passes the image through three convolution blocks. The first convolution layer contains 32 filters, the second contains 64, and the third contains 128. Each convolution block is followed by the batch normalization and max pooling. As we go deeper into the network, the number of filters increases, allowing the model to learn increasing complex visual features. After configuration, we use global average pooling to convert features maps into compact representation. Dropout is then used for regularization, followed by a dense layer with 128 neurons. Finally, the output layer contains 10 neurons with softmax, producing probabilities for our 10 classes. The complete model contains 11946 parameters.
Myself, Karan Bijapati, and I'll be doing the training configuration part. So in this, after finalizing the CNN architecture, we trained it using the training data set and monitor its performance using the validation set. We have also used the Adam optimizer with a learning rate of 0.001. The loss entropy we have kept as fast category cross entropy. We have used only a batch of 32 with a maximum of 25 epochs since we are working on our own system. So we have put the model compact. We have also used the early stoppings and model checkpointing to prevent unnecessary training. And if we go to the next slide, which is training and validation curve, here after We train, we check for the validation curve. So in this graph shows the model performance during training. Training accuracy generally increases as the model learns the images. If we see, however, the validation accuracy is more variable, this suggests that the model learns the training data well, but generalizing to new images is more challenging for this model. To help with this, we use augmentation, batch normalization, dropout, and training callbacks to control this overfitting. So we are focused on validation performance rather than training accuracy alone. If we go to the next slide, we can find the test results and metrics. After training, we evaluated the model on 687 unseen test images. We achieved an accuracy of 87.77% with a test loss of 0.3681%. The macro precision score was 88.33 and the recall was 88.66. The fun score was 87.89. Basically, the model correctly classified around 88 out of every 100 unseen images. The macro F1 score is also important because it gives equal importance to each diseases class instead of letting larger classes dominate the result. Then comes the confusion matrix. Here, the confusion matrix gives us a closer look at the was the model's mistake. The diagonal shows the correctly classified images, while the other value shows misclassification. The main confusion we can see is between the tomato early blight and the tomato late blight. If we give an example from this 52, tomato late blight images were correctly classified, while 14 were classified as early blight. So this suggests that these two diseases have similar features, making them harder for CNN to learn or distinguish. So the confusion matrix gives us more information than accuracy alone. So overall, the model performed well, but some diseases were still harder to classify than others. So next part will be carried out by Rishi, Rishi will discuss this class-wise results along with the limitations and real-world impact of the model. Thank you.
Let's look at the performance class by class. Our strongest class was Potato Early Blight with an F1 score of 94.81%, Grape Healthy with an F1 score of 94.31%, Apple Scab with 93.71%, Tomato Healthy with 92.5%, Apple Black Rot with 92.02%, Grape Black Rot with 90.65%. We also saw strong performances for Tomato Healthy, Apple Black Rot, and Grape Black Rot. However, early blight, tomato late blight, and potato late blight were more challenging. This matches what we observed in the confusion matter which we previously saw. These diseases have very similar visual features, particularly in terms of lesion color, texture, and shape, making them harder for the model, making them hard for the model to distinguish. Moving on to class imbalance and limitations. One limitation which we identified is that our dataset is not perfectly balanced. Most classes have around 305 training images, but Potato Healthy has only 106 images, while Grape Healthy has 296 images. This means some classes have less representation during training. In the future, we could address this using class weightage or targeted oversampling. There are also other limitations. Plant villages are relatively controlled compared to real field photographs. Also used only 10 classes, and our model predicts the disease type but does not estimate the severity of the disease which we predicted. So, our current model provides a good baseline, but there is still a gap between the experimental setup and real world deployment. In conclusion, we developed a custom CNN for 10 class plant disease classification across tomato, potato, apple, and grape plants. The model achieved a 87.77 test accuracy and 87.89 macro F1 score on 687 unseen test images. It performed particularly well on classes such as potato early blight, apple scab, and grape healthy. And the main challenge was distinguishing visually similar diseases, especially tomato early blight and tomato late blight. Overall, our results show that even a I'll just start this. Overall, our results show that even a relatively compact CNN trained from scratch on CPU hardware can provide a useful baseline on plant disease screening. And coming to the future work, like how we can work on it and improve it, if we take this project further, there are several improvements which we can make. First, we can handle class imbalance using class weightage or targeted oversampling, which I had previously mentioned. We could also use transfer learning with models such as MobileNet or EfficientNet. which may improve accuracy while remaining computationally efficient. Finally, we could expand to the full plant village taxonomy, test the model on real field images, develop a mobile or web application, and add disease severity estimation. Moving on to the references, these are the major papers. These are the major papers and the plant village dataset what we referred to while developing a methodology and understanding existing CNN based approaches for plant disease detection. Okay, just mess me again. Yeah. So this brings us to the end of our presentation. We covered the complete pipeline from image pre-processing and CNN training to evaluation and performance analysis. Thank you for listening.